Hi there! Welcome to your lesson on completing the square. Let's get to it. You can see this square being completed. That's exactly what we're going to do in this lesson. Let's do it. So, are you familiar with algebra tiles? Maybe, maybe not. Here's how they work. Imagine these little plastic pieces in your hand, and there are basically three sizes of plastic pieces. There is what is called the unit piece, which has dimensions 1 by 1, and we say has an area of 1. It's just a square, 1 by 1 square. Then there's these pieces that look like this. Notice it has the same width as this one. Therefore, we say it has a width of 1, but it has some unknown length here. We call that x. Therefore, the area of it is x. So we call that the x tile, because 1 times x is x. Now, there's one more piece. It is another square, but this time it has the same side length as this one. So that means its sides are x by x because it's the same as this. So it has an area of x squared. With these three pieces, we can do many algebraic things. Let's try something. Let's say we have this situation. In this example, I can see some algebra tiles laid out here. We have one x squared tile, 4 of these x tiles, and then 4 single unit tiles. Question is, these tiles combined here together represent what quadratic expression? Well, clearly they represent. Now, and at the heart of this lesson is this idea. Can we take these pieces and make a perfect square? Can you rearrange these to make a square? So let me show you what I mean by that. We can take the x squared piece, lay it here, and notice that the x pieces have the same length, right? So we can lay 2 of them here, and we can lay the other 2 here. So we basically split these in half. 2 of them, there's 4, half of them go here, half here. And now we have these gaps here for, well, the single unit pieces. So check it out, all 4 are there, fill that perfectly. So these are rearranged into a perfect. Now, let's consider that perfect square. In that perfect square, how long is this side? Well, or let's go this one first. This has a length of x, this is 1 unit here, and this is 1 unit here. And on this side, we have the same thing. This is the length of x, this is 1 unit, this is 1 unit. So how long are each of these sides? If you had to give it a length, how long would that be? Well, that is x plus 2. And how long is this side? Also x plus 2. So we have made a perfect square with side lengths x plus 2 and x plus 2. Therefore, we know that this original expression, these pieces, can be rewritten as x plus 2 squared, because those can be rearranged as this perfect square, x plus 2 squared. And in the past, we would say that we have factored that from there to there, and that makes sense. It is factored form because now this is something times something, and we have it here. All right, let's try this one here. We have a bunch of algebra tiles here. Can you first write an expression to represent these? Okay, that expression is x squared plus 6x plus 9. Okay, we have an x squared, 6 x's, and 9 units. All right, so now, second step. Can you take this and draw it on your page as a perfect square? So can you rearrange these so that we can create a perfect square like we did in the last one? Let's see. Here's our x squared. I see 6 of these x blocks, so I always know I have to split that in half, which is 3 along here, and then 3 here. And then I have this gap, and this gap we can see is a 3 by 3 gap, so I need 9 unit pieces, and that's what I have here, exactly 9 of those, so they fill that space perfectly. So we have shown that this can be rearranged as a perfect square, so that means this must be a perfect square trinomial. And here we have x, 1, 1, 1, so that side has a length of x plus 3, so does this side, so we know that factored form must be x plus 3 squared, because it's x plus 3 times x plus 3. Great, perfect square trinomial, factors like that. Try one more. How about this one? What's the expression for what the tiles we see here? Well, that expression is x squared plus 8x. Now there's no single units. Interesting. Okay, so try to rearrange this as a perfect square. Well, maybe you tried this. You have x squared, and then you have 8 of these. So I'm going to split that in half and put 4 along the top, 4 along the side, and I have done what I can. There's no other pieces. We have this gap like we had before, but we can't fill it because we have no units, no single units. So that tells us this is not a perfect square trinomial because we can't make a perfect square with it. However, we can do what's called completing the square, and that's what this lesson is all about. We can add some number here to make this a perfect square trinomial. That process is called completing the square. What number do we need to add there? How many single units do we need? Well, this is 4 by 4, so we need 16 single units. So if we just added 16 to that, we have created a perfect square trinomial, or we have completed the square. That's what we did here. And when we complete the square, we can now factor it using the shortcut we know. This is x plus 4, so that means this factors into x plus 4 squared. So this is the heart of the lesson here. This began as a non-perfect square trinomial. We found a number that we can add to complete the square, and therefore we have a factoring that can be done like this. All right, let's look at this algebraically. So we made this, let's just recap what we just did. We had this first one here, but now I'm making it an equation, right? We had this one here, and we noticed it's a perfect square because it can be rearranged as a square, and it factored like that. Great, perfect square is factored like that. The second one, we had this set of tiles, and we noticed also it's a perfect square because we could rearrange it and make a perfect square, and it factored like that. And the last one, we had this. We had to add 16 to it to complete the square and make it a perfect square trinomial, and then we can factor it like that. That's the journey we've taken so far. Let's try it here. So let's factor each of these, noticing that they are a perfect square trinomial. So is this a perfect square trinomial? I want you with these to use your vivid imagination and try to imagine these as the algebra tiles and rearrange them in your mind as like the square and then the other pieces. So something like this. So for this first one, we have x squared. So imagine we have x squared. And this is 14. So remember, we always split that in half. So we put 7 here, 7 here. So 7, and I put them just as lines now, but remember those were like the long rectangles. 7 of them here. And then x, we have 7 more x's here. And then that leaves a gap. And that gap is 7 by 7, which is 49, which we have here. So we know, thinking of this one, in our minds, we were thinking 7, 7, this has to be 49. Oh, good, it is 49. So it's a perfect square. So it must factor like this. This one here, try to imagine this as well in your brain. All right. How many of these will you have along the top if you're imagining it like this? Well, it will be 6, right? It will be 6 here, 6 here. Therefore, we'll have a 6 by 6 gap, which means 36 is perfect. This is a perfect square. Therefore, it must factor into x plus 6 because you would have x plus 6 pieces, and here also. Last one, what will that factor into? X plus 4 squared. All right, hope you're getting the hang of it, and I hope the visual bit is helping you see this in a different way. Let's try some, question. How do we get the number of units? Well, that's what I've been talking about. How do we get this number of units? Remember, we just lay these out here. We take that number, split it in half, and then we know that we have a square of that is the number of units, right? 14 divided by 2, 7 squared gives us that units. Same here, same here. Okay, try with some negatives now. Even though we have negatives here, it kind of works the same way, right? Imagine setting up the square. This is 10, so we have 5 here, 5 here. How big will the gap be? If it's 5 x's and 5 x's, the gap will be 25. Perfect, perfect square. Factors like this. With that minus sign, we now have a minus. How about this one? This one factors to x minus 6 squared. Divide this in half, because you'll have 6 here, and a gap of 36. So x minus 6. And last one, x minus 2. Great. I hope you really have the hang of it. Let's keep going, because this is kind of a refresher on something we've done, but thinking of it in this visual way. Okay, let's take a look at this here. So we have all these expressions. These are not perfect square trinomials. Remember, sometimes they begin as not a perfect square, and we want to make it a perfect square. So let's remember the process. If you arrange these with little algebra tiles, you would have your x squared. You would have 3 across here, because this 6 is divided into 3 and 3. And then you have the gap that you need to fill with the single units. So that gap is 3 by 3, so 9. All right, that's how we do it. We take this number, divide it by 2 to get 3, and then square it. That's how we get the magic number that turns us into a perfect square. So what will be the magic number? Oh, actually, before that, now that it's a perfect square, we can factor it. X minus 3, and this is x minus 3 because we have a minus sign. So it's x minus 3 squared. Try the same thing here. What's the magic number? 64. We took that, divided it in half, so we would have like 8 by 8, and then 8 squared. 64, okay? This divided by 2 and squared, easy. All right, that then factored is x plus 8 squared. How about this next one? Okay, magic number 100. This divided by 2 and squared. Factored form, x minus 10 squared minus here, minus 10. How about this one? 144 and x plus 12 squared. How about this one here? 169 and x minus 13 squared. This one here, 25, x minus 5 squared. This one, 1 and x plus 1 squared. And this one finally, 400. We took this, divided by 2, we squared it to fill that gap. We have 400. And that is now x plus 20 squared. I hope the visual has added a whole new element to these for you. Okay, so the question and a key conclusion now, how do we get this magic number? Imagine we have a standard form quadratic with an a value, a b value, and a c value. A, b, and maybe no c value. How do we get this magic number? We get it by doing this, b over 2 squared. We take that b value, we divide it by 2, right? So we did the 6 here, divided into 2 parts. And then we have 3 by 3, 3 squared. So this divided by 2 squared gives you the magic number to create a perfect square. Awesome. Let's move on. So making a perfect square. Summary, we have this quadratic equation. It is not a perfect square trinomial. We need the units. We think of a perfect square. Now these lines don't match what we have here, but this is 20 divided by 2. So imagine this is 10 of those, 10 of those. We have this gap. And if this is 10 by 10, the gap is 100. And the way we get that gap again is 20 divided by 2, 10. And we square it because we're creating a little square here, 10, 10 squared. 100, magic number 100. And the formula, then that means this can factor into x plus 10 times x plus 10, because we have two sides of a square, which is x plus 10 squared. Okay, standard form, another form here. So the rule, b over 2 squared. Okay, remember this rule, the rule for finding the magic number to turn a quadratic into a perfect square. Let's keep going, because now we're taking this a step forward. We've talked about quadratic functions in different forms: standard form, vertex form, and intercept or factored form. We know to change from standards to vertex form, let's label those, standard to intercept form, we just factor. We know to turn from vertex to that, we multiply this out, But today's lesson is really about this. Let's say we have a standard form quadratic. Can we turn it into vertex form? And this is what completing the square is all about. Let's take a look. So change to vertex form by completing a square. The method we've learned is going to be helping us do this. So we have this standard form quadratic. This is not a perfect square trinomial. Okay? But here's what we can do. Now make sure you write down this process for sure. We can take that 1, move it over to this side. So we have y plus 1 equals this. Now we have this expression that is not a perfect square, but maybe we can make it a perfect square. We just learned how to do that. The rule is b over 2 squared. This value divided by 2 squared. 10 divided by 2 is 5. Square that, 25. So the magic number we can add on this side to turn this into a perfect square is 25. So we're adding 25 here. And if we're adding 25 on this side of the equation, we better do it over here, because when we have an equation, we have to do the same thing on both sides to maintain the balance. So added 25 and here also. Now this side is now a perfect square trinomial. So we know it can factor like this, x plus 5 squared. Notice all of a sudden we've turned this from standard form to vertex form, because now we have this 26 here. We can move that 26 back here, and there it is. That is now vertex form. You may remember vertex form looks like this, x plus h squared minus k. This is now vertex form. Standard form, vertex form. So we have used completing the square to make that change. Make sure you really pause and understand these steps, because these are the basics, and we're going to try some harder problems right now. So let's try another one. Here's this one. How about give this a try? You just saw the process. Can you do it? Okay, let's check our work. The 7 moves over here. Now we're left with this expression on this side. Let's turn this to a perfect square by doing b over 2 squared. So negative 6 over 2 squared. We're dividing that in half, squaring it. It is 9. So we are going to add a magic number of 9 here and here on both sides. That magic number has turned this into a perfect square. Therefore, it factors like this. Now there's a minus sign because we have a minus 6. On this side, I combine negative 7 and 9 to get 2. Move the 2 over. All right, so what we have is this. We turned a standard form quadratic into a vertex form quadratic by completing the square. Let's do this on a problem that's slightly different. This one here, we have standard form. However, we notice that the a value is no longer 1. It is now negative 1. Whenever the a value is not 1, we need to do a little bit more in the process. Let me show you. So here, I did the first step, sorry. Move the 6 over here. Now I have this expression. Now, when I have this negative here, I need to factor it out. So I'm factoring out a negative from both of these terms here. So I took a negative out, this became positive, this became negative. Now that I've turned this a value into 1 here, I can proceed with the steps we've used before. So for this, I'm going to find the magic number that makes this a perfect square. What is that number? Well, we do b over 2 squared. So negative 8 over 2 squared is 16. So now that magic number will pop in here and here. So we know we're going to write 16 here. But what are we going to write here? Well, in the past, we would have written 16 here also. But now, and this is important to know, we have this negative here. So if we took this negative and multiplied it back through here, what we actually added to this side is a negative 16. So that means we need to put a negative 16 on this side also. It's important to consider that in front of all this. So now this maintains the balance. Now let's continue. Negative 6 minus 16 is negative 22. This is now a perfect square trinomial. So we have negative, and then x minus 4 is this factored as a perfect square. And move the 22 over, and we have our vertex form. So we took our standard form, changed it to vertex form. Notice we still have negative a value. That means it's a concave down parabola. Excellent. Let's try some more. So you're going to try these two. Based on what you just learned about changing a standard form quadratic to a vertex form, use completing the square to change both of these to vertex form. Notice this one is just 1 here, and this one has that negative there. So try this one first. Okay, and now try this one. All right, check your work. Here's the first one. All the work is shown here. Notice we have the 49 here. It's here. Solving. It's that. Pause and check your work carefully if you need help with that. But something I wanted to point out. Let's just confirm that these are actually the same parabola. So looking at the bottom one, or actually looking at the standard form, we know we can find the vertex by, down at the vertex form, we know the vertex is this number and this number, negative 7 and negative 55. Now from standard form, we know we find the vertex by doing negative b over 2a to find the x value. Negative b over 2a in that case is negative 14 over 2, which is negative 7. Notice that the x value we get using this little formula here is the same x value we see in this vertex here. So we've kind of confirmed that it's the same parabola we're still dealing with here. Let's look at the second one. Here's the second one with that negative sign that you tried. Remember, we have to factor out the negative. That means when we add the magic number of 81 here, it has to be a negative 81 here because of that negative affecting this. Simplify, vertex form. Let's take a look. Standard form, vertex form. Here, what is the vertex? Oh, it is 992. Therefore, here, let's confirm it's the same vertex. Vertex negative b over 2a to find the x value, negative 18 over negative 2, and 9. Notice the x value is the same. We've confirmed it's the same equation, just different forms. All right, one last thing you need to learn is what am I writing here? It should say, what if the a value is greater than 1? So check out this one here. The a value is now 4. We've seen what happens when we have a negative there, but what happens if this is just not a 1 at all? It's a 4. Well, it's going to be a similar process. Let's take a look. Here's our standard form. I'm going to move the 13 over first, right here. Add 13. Now, I want to make a perfect square out of this. But before that, we want to factor out. Remember, when a is not 1, we want to factor that out. So I'm going to factor the 4 out right here. And now this is x squared plus 8x, because I factored 4 from both of those. Now that we have a is 1 here, now we can use this as our perfect square. So find the magic number you're going to add here. What is it? b over 2 squared, 8 over 2, 16. The magic number is 16. So over here, we're going to add 16. What about here? It's not 16, it's 64. Just like when we had the negative here, and we had to then makes this a negative number, we always need to consider what's here, because now if we multiplied 4 by all of this, this would not be a 16 anymore. This would be a 64. So we've actually added 64 on this side by putting this here. That means we need to add 64 here to maintain the balance. Continuing on, this is a perfect square now. It is factored into this. Move the 77 back here. We have our vertex form. Fantastic. Pause if you need to. Consider everything carefully. Last two for you to try. These two here. Try to change this to vertex form. Remember now that a is not 1 right here. Okay, now try this one. This one's going to be trickier. You might have some decimals here. Let's see if you can do it. Okay, here's the first one. Taking a look at all the work. I'll just show it all right here. Okay. The 2 was factored out here. Therefore, magic number 9 is here, but then it's 18 here because it has to be 2 times that 9. Continuing on, there's our vertex form. And the second one, this is the one that has some decimals. Pause, take a close look. A little more challenging with decimals for sure, but I hope at this point you got the process. Great job. We'll see you soon.